this next section, we're going to look at partial derivatives. So, as I mentioned in the last section, we're going to be doing a lot of the same things we did with functions of one variable that we're going to do with functions of several variables. And so one of the notions we had back at towards the beginning of this course was looking at a function and its rate of change, or looking at the derivative. So here, if we recall, when y was equal to f of x, we said dy dx was the derivative of f, or it's the rate that y is changing with respect to the variable x. Meaning if I'm looking at the function f, it's the rate it's going to change in the x direction. Okay? A partial derivative of an n-variable function is the rate that the function is changing with respect to a specific variable. So now, because we have more than one variable in the function, we no longer have just the derivative. We now have what we call partial derivatives, which gives us the derivative in a particular direction. And so the best way to think about this is if I'm looking at a three-variable picture, whatever my graph is, I'm going to pick kind of a nice simplified one. Let's look at kind of an upside-down bowl. I'm going to get rid of these lines so maybe it's a little easier to see. So here's my y, here's my x, and here's my z. Okay? So if I'm looking at this, I can think of picking a point on this upside-down bowl, and if I'm talking about the derivative, I can think about the rate that z is changing in the y direction. So we've got some component in the y direction where it changes, or I can talk about the rate that z is changing in the x direction. Okay? So with respect to each of the variables, I can come up with a partial derivative. It's a rate of change. Okay. So let's consider a two-variable function. So again, you can think z equals f of xy, or just f of xy. Then the partial derivative of f with respect to x, we have two different denotions for this. The first is our Leibniz notation, just like we had with the one-variable function, so dy dx. Here, this cursive d, this is our representation for partial derivative. So the partial of f with respect to x, or we can denote it this way. I'm looking at the function f, and I'm taking the first order partial with respect to x. This is the rate that f is going to change in the x direction when y is held constant. Okay? And likewise, the partial derivative of f with respect to y, again, same denotations. The rate f is going to change in the y direction when x is held constant. Okay, so let's look at some examples of some partial derivatives. In these first few examples, we're going to look at two-variable functions, and we're going to look at first-order partials for both of the variables. Okay? And then we'll move on to some slightly harder ones. So in this first case, this is just a nice function in the sense that there are no products of my variables. So I've got f of xy equaling 5x squared plus 2y cubed minus 7. Okay? And so here, if I want to find the partial of f with respect to x, and again here I'm going to write both notations so that you can get used to both notations. This just means I'm going to take the derivative with respect to x and leave y as a constant. Okay? So remember, anytime I take the derivative with constant, I get 0. So if there are no x's, but there are y's, then my derivative is just going to be 0. Okay? So here, if I look at this, my partial with respect to x means in this case I'm going to take the derivative like I normally would with x. So a 10x. Here, there's no x's, so that's just going to be 0. And of course, a constant is also 0. So here, my partial with respect to x is just going to be 10x. If I want to see my partial of f with respect to y, again, both notations being written there. Here again, this just means y is the one I'm going to treat like my variable. Everything else is going to be held constant. So, when I look at 5x squared, the derivative there is just going to be 0 because there's no y's in it. my 2y cubed becomes a 6y squared, and again my constant just goes to 0. So here my partial with respect to y is just 6y squared. Now again, this one is fairly nice because every term, my x's and y's are separate. So here I have x's and y's in both terms. Now again, it depends on how they show up in the terms. So same thing, I want to take each of those partials. So I'm going to look at the partial of f with respect to x. Okay. And again, in your homework, you can get used to just writing one of the two notations. Again, here I'm just going to write them both so you're familiar with both of them. In the case of 2x e to the y, if I'm trying to take the partial with respect to x, again, I notice that e to the y is just going to be a constant. So my derivative here is basically 2 times x times some constant. My derivative is just going to be 2e to the y. Okay. For my second term, 3y is going to be treated like a constant, and ln of x is going to be the variable part. So the derivative here, the coefficient just gets brought along, and the derivative of 1 over natural log of x is just 1 over x. Okay. So my partial of f with respect to x is going to be 2e to the y minus 3y over x. Okay. Notice in this case they don't go to 0, even though I have those y's in there. Here, because they're attached to an x term, they don't go away. Same or similarly, if I look at f sub y, I keep writing x's there. In this case, when I take my partial derivative, in this first term, the 2x is the constant piece, but it's like a coefficient here. So the derivative of e to the y, we know is just e to the y. So this is just going to be 2x e to the y. For the other part, the natural log of x is going to be treated like my coefficient. So my derivative of negative 3y is negative 3 times my ln of x. Okay? And there's my partial derivative for that one. Now in both cases, in your homework and on WebAssign, you're going to see some of these problems that ask you not only to find the partial derivatives, but also evaluate them for different values. So just like in the last video, when we talked about evaluating functions, they're going to say find the partial with respect to x evaluated at 2, 0. Okay? And so, for example, here, if I want the partial of f with respect to x evaluated at the point 1, 0, all this means is I'm going to take this derivative that we found, this partial derivative, and plug in 1 for x and 0 for y. So we would get 2e to the 0 minus 3 times 0 over 1. And we can simplify that. Notice that piece goes to 0. This is just going to go to 2. Okay? Again, for all of these, you're usually going to get some values, meaning some numbers. And again, it just works very similar to what we did before. Same thing if I want the partial of f with respect to y evaluated at 2, 2. Here again, we can plug in. So we'll get a 2 times 2e to the second minus 3 natural log of 2. Evaluating that, we get 4e squared minus 3 ln of 2. Okay. Again, a number, not pretty, but it's still a number. Okay. In these next few examples, we're still looking at partial derivatives, but now we're taking it a step further. So just like in the one variable, we had kind of the nice functions that we could take derivatives of using just basic properties. But then we extended that to things where we needed product rules, quotient rules, chain rules, and some of those other more involved derivative techniques. With partial derivatives, you're going to see some of those as well. In this course, we are not going to do implicit partial differentiation or logarithmic partial differentiation. So nicely, those two things are out. However, you are still going to be asked to do some product, quotients, and chain rules. Okay? So in this next example, here we're looking at some of the product rules. This is a three-variable function, so f of x, y, z equaling xy squared z cubed minus xy. And in this case, in order to solve, again, I'm going to have a partial derivative for each of the variables. So in this case, I'm going to have three partial derivatives. But again, when I go to treat the others as constants, I have to think, is it being treated like a coefficient or is it truly being treated like a constant? And this is where your product rule will come in. Okay? So here, if I want to look at the partial of f with respect to x, okay, it says y and z are going to be treated like either constants or coefficients. Well, in this case, x times y squared plus times z cubed, these are just coefficients because it's being multiplied by my x. So my partial there is just going to be y squared z cubed. In this case, same thing. That x is just treated, makes that y be treated like a coefficient. So there's my partial derivative. Okay. In the case of f sub y, again, the y squared, I'm going to bring that 2 down. So I'm going to have 2 times the x, y, z cubed. Okay, so those are treated as coefficients. They don't change. And we can see the 2y is my derivative of y squared minus x. And then lastly, for f sub z, in this case, xy squared is my coefficient. My derivative of z cubed is 3z squared. And on the other end of that, there's no z, so that's a constant. That's going to go away. So there's my partial with respect to z. In this next example, f of xyz looks like the cubed root of 2xy minus yz squared over x plus y plus z. Okay? So this one's got a little bit of our quotient, our product, and our chain in there. Okay? So again, let's start with our f sub x, or partial with respect to x. Okay? So here, first thing to notice is I have x both top and bottom, which means I'm basically looking at a quotient rule. So my quotient rule says I'm going to do the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. Well, in this case, my derivative of the top requires a chain rule because I have that cube root outside of everything. So my cube root looks like a 1/3 times the inside to the negative 2/3, okay, times the derivative of the inside, which in this case the x is the only thing that's treated like a variable. So that first term is just going to be a 2y. That second term is going to go to 0. That's my derivative of the top times the bottom minus the top times the derivative of the bottom. Now here I've got some plus signs. So the derivative of the bottom with respect to x is just going to be 1 plus 0 plus 0. Okay? All over the bottom squared. Okay. These functions are going to be a little bit more difficult to clean up, but they work very similar to what we did before. So in this case, I'm going to start by getting rid of the negative exponent on the top. So notice that's 1 over that, so I'm going to need to multiply by an x, 2xy minus yz squared to the 1/3. Okay? Sorry, to the 2/3. So, and I've also got this 3 there, so I'm going to multiply that by 3 too. So I'll get a 2y x plus y plus z minus a 2x y minus yz squared multiplied by 3, so multiplying by that denominator that we just had. And then on the bottom, x plus y plus z quantity squared times this piece that we had here. Okay. And there you can see there's not a whole lot we can do. We can clean this up and combine some like terms. So we'll have a 2xy minus a 6xy. This looks like negative 4xy. There's a 2y squared and a 2yz. And then over here plus a 3yz squared. And that's all over this denominator. So there would be my partial with respect to x. Okay. Now you can see the process for these is very similar to what we did before, but because I now have more variables and I'm looking at different, treating different variables as constant and so forth, my products and quotients become a little bit more long. Okay. Let's do the same thing for f sub y. Okay. So for f sub y, we can see here that, again, I have y's both top and bottom. So I'm still going to need to have a quotient rule. Okay. So again, for the top, the start is going to be very similar because, again, my quotient, my chain rule on the top says it's going to be 1/3 times the inside. Now times the derivative of the inside. This is where it's going to change a little bit because now y is my variable, x and z are constants. So I'm going to get a 2x minus a z squared, okay, times the bottom minus the top times my derivative of the bottom. And again, x and z are constants, so my derivative there is just 1. Okay, all over bottom squared. Okay, and again we can get rid of the denominator or the negative exponents just like we did before. So again, we'll multiply by 3 times this to the 2/3. So we'll get a 2x minus z squared times an x plus y plus z minus 3 times 2xy minus yz squared all over 3x plus y plus z squared cubed root two xy minus yz squared to the 2/3. Okay, again, cleaning this up, so we're going to do some distributing here. We'll get a 2x squared plus a 2xy minus a 6xy. We'll get a 2xz minus an xz squared minus a yz squared plus 3yz squared minus a z cubed. And again, that's all over that denominator. Lastly, if we want to look at f sub z, same thing. So z's top and bottom mean I'm going to need a quotient rule. So on the top, the derivative 1/3 2xy minus yz squared, the negative 2/3 power times the derivative of the inside. First term doesn't have any z's, so that's just going to be 0 minus a 2yz from the derivative there with respect to z. That's times the bottom minus the top times the derivative at the bottom. All over bottom squared. Okay. Again, cleaning it up. So again, we'll multiply by 3 times that negative 2/3 expression. So we'll get a minus 2yz times an x plus y plus z minus 3 2xy minus yz squared all over 3 times x plus y plus z squared 2xy minus yz squared to the 2/3. Okay. Again, combining like terms, so we'll get a negative 2xyz minus a 2 y squared z. We'll get a minus 2yz squared plus 3 of those minus a 6xy. And again, that's all going to be over that denominator. So there would be our partial with respect to z.